So we talked about those degree measurements of 30, 45, and 60 quite a bit when we looked at angle measurements. What we're going to do is tie some of those properties to our right triangle, and then tie some of those properties to our trig functions. This is all building up to our unit circle, so we'll talk about these pieces again. I just want to make sure while this information is pretty fresh, it's better to see it multiple times, especially while it's fresh, and then we'll tie it in next week as well with these. So what we're going to do is look at two special triangles. First, we're going to look at the 45, 45, 90 right triangle. And what we want to do is essentially solve the triangle. So when we say solve the triangle, that means to find all angle measurements and all side lengths. One thing we're going to need though is we're going to need a side length to start with. So when we work through this, we're going to be working with a hypotenuse that's equal to 1. So with the 45, 45, 90, I'm going to say that side length there is equal to 1. Same thing when we get to this 30, 60, 90, I'm going to say that side length is equal to 1. And that's going to tie into our idea of a unit circle later on. All right, 45, 45, 90. So what that's telling me is that we have an angle measurement of 45 degrees. And if one of the angles is 45, then the other angle also has to be 45, so that all three angles add up to 180 degrees. Now, in a triangle that has two of the same angle measurements is called isosceles, and that means that these two unknown side lengths are exactly equal to each other. So we have these same side lengths showing up, and we don't know what they are yet, so for right now, I'm just going to call them x, but I need to solve for them. But since they're the same, I get to use the same variable for both sides. So now what I'm going to do is to solve for the side length, I'm going to use the Pythagorean Theorem. So we have this hypotenuse of 1. I'm just going to label that that's our hypotenuse. A hypotenuse of 1, and then these legs equal to x. So using Pythagorean Theorem, we would take one leg squared plus the other leg squared, and that should equal our hypotenuse squared. So x squared plus x squared is 2x squared, and that equals 1 squared, which is 1. Divide both sides by 2, so that'll be a 1/2. And then to solve for x, I'm going to take the square root of both sides. So x is equal to, so the square root of 1 is just 1 over square root of 2. And then something I'm going to do here is rationalize the denominator. So it may have been a while since you've done this, and it's really just a formatting thing. So rationalizing the denominator is multiplying by something to get rid of the radical in the denominator. So the idea is if I multiply that denominator by a square root of 2, then I'm just going to get 2 out. But I can't just multiply by any number. I'm simplifying here, so I would need to multiply by a version of 1. So I'm just multiplying by root 2 over 2. This won't come up all that often. I just want to explain what I'm doing so that you can see the format of this number. So x equals, in the numerator, we'll have 1 times the square root of 2. In the denominator, root 2 times root 2, that's like the square root of 4, but that'll simplify down to just 2. So 1 over root 2 is exactly equal to root 2 over 2. This just doesn't have a square root in the denominator, which is typically easier for simplifying. So all of that work was done to find our missing side length, and we found that it is the square root of 2 over 2. So, what is this and why are we doing this is a big question, and it does all tie in together. But basically, this is a special triangle that we want to keep in mind. And it's a triangle that's specific to having 45-degree angles in there. And it's very specific to the fact that we have a hypotenuse of 1. As you can imagine, if we change that hypotenuse there, these numbers would change as well. But in the future, we're going to be working with these triangles specific to having that hypotenuse of 1. So this is just a triangle we want to keep in mind. But I wanted to show where those numbers came from rather than just showing you the square root of 2 over 2. Maybe some of you would have just been happy to believe me, but I wanted to show you where it came from. And now we're going to do the same thing for 30, 60, 90. So this is our 30, 60, 90 right triangle. And what I'm going to notice is up here is the smaller of the angles. So I have these 2 angle measurements. I have this kind of big one, small one. So 30 degrees is going to be the smaller measurement. 60 degrees is the larger measurement. All right, so we're going to have 2 side lengths here and 2 unknown side lengths. So I'm going to call these x and y. Something I want you to notice though is that with this 30, 60, 90, one of the unknown side lengths is quite long. So there's this long side and there's this short side. And that's something that I like to refer to a lot when we get into the trig functions and using them, is that once we get through this, I'll show you the decimal approximations. I just try to keep in mind which is the long side, which is the short side. So let's go ahead and call the long side y and the short side x. Now, to solve, I can't just jump into the Pythagorean theorem because I have 2 unknowns. And I don't have a way of relating those 2 unknowns with each other quite yet. So right now I'm kind of stuck. So what we're going to do is use this little picture I put here, in that we're basically going to reflect that triangle. And just imagine they're perfectly touching right there. I couldn't get the computer to completely merge them, but imagine they're touching. So we have this hypotenuse of 1, and same thing over here, hypotenuse of 1. And then it's like we have x, and then for the height, we have y. And we have 60 degrees, 60 degrees. And up here, if we combine the 30 and the 30, that is also 60 degrees. And what this is an equilateral triangle. So an equilateral triangle has 3 angle measurements that are exactly the same. So that's where we're seeing the 60, 60, 60. And with that brings through the property that all 3 side lengths on the outside of that triangle are equal to each other. So our 3 side lengths, we have the 1, and what this is telling us is that along the bottom here, this is a total distance of 1 as well. So this right here is a distance of 1. Well, if 1 is made up of these 2 x values, then that's telling me that x needs to be equal to 1/2. And same thing over there, but really we just need one of them. So from that equilateral triangle property, we're seeing x is equal to 1/2. So with that can fill in the blank down here. So that's our short side is 1/2. Now to solve for the long side, we don't really need to use that equilateral triangle anymore. That helped us get the 1/2, because now we have a right triangle where we know 2 of the side lengths, but we're missing 1 of the legs. And with that, we can use the Pythagorean theorem. So our hypotenuse is 1, and then we have a leg of y and leg of 1/2. So we're going to have leg of 1/2 squared plus leg of y squared equals the hypotenuse squared. 1/2 squared is equal to 1/4. This is just y squared, and 1 squared is equal to 1. I'm going to subtract 1/4 from both sides. 1 minus 1/4 is 3/4. If you're having trouble with fractions at all, just to make sure you know what we have here, so like 1 minus 1/4, Desmos can be a good support. So this gives a decimal. I definitely want to keep things as a fraction right now as I simplify this. And Desmos has this convert to fraction. and it will always give you the reduced form of the fraction. So as we deal with fractions with this class, use that as a support, since we kind of, at this point, assume you have the fraction arithmetic down, but fractions are hard. I won't sugarcoat that. So having Desmos as support can be very helpful there. All right, and then I'm going to take the square root of both sides, which will give me y equals, so in the numerator, square root of 3, in the denominator, square root of 4, which simplifies to a 2. So with that, we just found the long side of this triangle, which is the square root of 3 over 2. Now, me saying short versus long, we could double check that with our kind of decimal value. So 1/2 is equal to 0.5. And the square root of 3 over 2 with the decimal approximation is a 0.8, about 0.87 is close to where it's landing. So with that, you have this idea of short of about 0.5, long of about 0.87. Our hypotenuse is 1, so they both should definitely be shorter than 1. And I'll go ahead and write the decimal approximation for square root of 2 over 2. It's just numbers that I kind of like to keep in mind as we deal with these as exact values. So this is about 0.71. All right, so these are two special triangles. This is something we're going to refer to a lot throughout our work with trigonometry as we deal with these 45, 30, 60 degrees measurements. These side lengths are going to be coming up. So with that, let's look at some of our trig functions using these special angles. So what I'm going to do is I'm going to take you through how I draw a sketch of these. So the 45, so with that I draw a right triangle and I try to make the angles as similar as possible. So this is my 45, 45, 90. And with that I can fill in the side lengths, 1, root 2 over 2, root 2 over 2. And as we deal with the unit circle, you'll have more practice of memorizing the root 2 over 2 piece, but for now, you can refer to the picture to help out. With the 30, 60, 90, what I do is we just need a long side and a short side, and we're just sketching here. I just want a graph I can easily refer to. So 30 will be in the smaller part, 60 will be the larger part, and then we have our 90. And then we'll have hypotenuse of 1, short side is 1/2, long side is root 3 over 2. All right, so with those sketches, let's look at sine, cosine, tangent. And since these are still fairly new, let's go ahead and make our note. So I'm going to make the note that sine is opposite over hypotenuse. So again, that SOHCAHTOA. That's something I remember when I was learning trigonometry, I just wrote SOHCAHTOA on top of every single homework and paper. And so if you need to do that, absolutely go for it. And I would draw the sketches of these triangles a lot. So I'm kind of visual and it can help to have those to refer to. So sine of 45 degrees, so with the 45, 45, 90, it doesn't matter which angle you're standing at because it's the same. So opposite and adjacent. So let's imagine we're right down here, which would mean we'd have opposite, adjacent, hypotenuse. So that means sine of 45 degrees is going to be equal to our opposite side, which is root 2 over 2, divided by the hypotenuse, which is 1, which means we're just getting out root 2 over 2. And that's going to happen with these ones where we're dividing by the hypotenuse. It just kind of goes away. So all we're really left with is that opposite side. Now let's say we wanted to check this answer. We plugged in this angle measurement of 45. We took opposite and adjacent using this triangle here. But if we wanted to check it, we can use a calculator. Now, the input for these functions can be in a measurement of degrees or radians, and that's where this button comes in. Now, if you have a physical calculator, it's usually under mode. You can change between degree and radian modes. On this calculator, you can see this is in degree mode. If I click it, it changes to radians, but right now I want to be in degree mode. So you can see your functions here, sine, cosine, tangent. You could also type them in with your keyboard, but I want to look at sine of 45. And right there is my decimal approximation for that square root of 2 over 2. I'll just show it so that you can really see that they're exactly the same. So this evaluation of sine with a 45-degree angle is coming through based on this triangle that's made with the hypotenuse of 1. So there's this relationship here that with that hypotenuse of 1, the ratio of opposite and hypotenuse will come out to that root 2 over 2. For sine of 60 degrees, so sine again is opposite over hypotenuse. And with this one, if we're at 60 degrees, opposite is the root 3 over 2 and then hypotenuse of 1. So that means the sine of 60 degrees is root 3 over 2. And we could check that in the calculator, again, looking at sine of 60 and seeing that about 0.87 is correct. All right, cosine of 45 degrees. So that's our adjacent over hypotenuse. So the 45 degrees, root 2 over 2 over our hypotenuse of 1, which means that will just be that root 2 over 2. All right, cosine of 30 degrees. So again, adjacent over hypotenuse. So if we're at 30 degrees, so if I focus right here, adjacent is the root 3 over 2, 1 is the hypotenuse. So this will just be root 3 over 2. Tangent, opposite over adjacent. So with the 45-degree angle, the opposite side would be the root 2 over 2. Adjacent would also be root 2 over 2. So this ends up being the same value. So for our ratio, we get 1 out. So the idea being that if you're comparing an opposite and adjacent side length to each other, when you're in a 45, 45, 90, well, those side lengths are always going to be exactly equal to each other. So that gives us this ratio of 1, showing that equality between the opposite and adjacent side lengths. When we look at the 60-degree angle, though, it'll be different because the side lengths one will be long and one will be short. So with this one, if we're at 60 degrees, opposite is the root 3 over 2, adjacent is the 1 over 2. So tangent of 60 degrees is root 3 over 2 over 1 over 2. And basically to clear out those denominators, it's like I'm multiplying both the numerator and denominator by 2, which would just give us the square root of 3. All right, so finding sine, cosine, and tangent of these specific angles, so 30, 45, 60, we're going to want to be comfortable with those, and these values with these radicals and fractions kind of mixed together all stem from these right triangles, so these special right triangles that we're working with. So what we are going to do is make a short connection to our unit circle here, seeing how this is going to tie into next week when we really dive into the unit circle. But the idea is, like, we kind of looked at these angles already when we talked about angle measurements. So we have our 45, we have our 30, we have our 60. What we want to start doing is talking about these coordinates that are along the outside of this circle. And specifically, our unit circle which is where our radius of the circle is equal to 1. And that's why we made that hypotenuse of 1. So let's see how this ties together. So if I draw a nice right triangle right there, and I know that this is 30 degrees. And then as we deal with this too, we'll talk about what happens. So we change this to radians. So that would just mean that this is pi over 6. But for now, as we talked about with our right triangles, we'll just kind of focus on this. So right triangle. So this is my 30, 60, 90. I can see my long side length here, and we can even see this is landing at about 0.87, which is what we estimated. And that's going to make our x-coordinate. So I want this x-coordinate and y-coordinate, and the x-coordinate is coming from this distance. That's the root 3 over 2. And the y-coordinate is coming from this distance, which that's the short side length. And again, sorry, I kind of skipped over this, but this would be 1 along here because we have this radius of the circle of 1. So with that, we know we have these side lengths root 3 over 2, and then the short side length would be 1/2. So the idea being when we get to our unit circle, if we're dealing with 30 degrees, because of these special triangles, we know those coordinates. Then we can go to our next one. Let's say we're making a triangle right here. So that right there is our 45-degree angle. And then I have my right triangle, and then hypotenuse of 1. Well, then with that, I can find my x and y coordinates based on that 45, 45, 90 that we just found. We know this distance is root 2 over 2. We also know that that distance is root 2 over 2. And that would give me those coordinates along the unit circle. So I have my x and y coordinates. And then our last one, sorry, get those out of there. All right, our last one would be up here. And this would be our 60 degrees. Right triangle with the hypotenuse of 1. So x and y coordinate, the x coordinate would be coming from the short side, which is 1/2. The y coordinate would be coming from the long side, which is the root 3 over 2. So we're going to talk about this so much more, but I wanted to tie it in while these triangles are fresh in our head and how it's going to lead to coordinates along our unit circle. But right here, we're pretty much started with filling in almost all of our unit circle because then the rest just come through with reflection. But in terms of getting our key values to start off our unit circle, it all comes from those two triangles that we just solved for.